Good day, everyone. I would like to start by saying thank you for joining us on this technical topic today. Can everyone please disable their notifications by simply going to my settings, the cog symbol in the bottom right-hand corner of the screen, as depicted on the screen. Go to notification settings and untick all the boxes on the screen. I'll leave this for a few minutes for everybody to do this process if you haven't done it yet. Today's technical topic webinar is Introduction to Hazardous Areas and HA Classification. It's a repeat because it has happened before. So for those that were not there for the first one, this the same one is just repeating again which will be presented by Miss Alexandra Gregory. And our letter, okay. Common questions asked. Within the next 2 business days, everyone who registered for this webinar will get an email with a copy of the PDF slides and a link to the video recording. Please keep an eye on your junk email folder. For live participants of technical topic webinar, we give a complimentary digital certificate of participation. At the end of this session, there will be a link and a QR code to a short form that you must complete in order to obtain one. Once finished, we will make every effort to mail your certificate to you within 4 business days. About EIT. If you are new to our webinars, here's some information about EIT. We are one of the world's only engineering-focused institution. We presently offer a variety of industry-focused courses, mostly in civil, mechanical, electrical, and industrial automation engineering, ranging from short courses to a Doctor of Engineering degree. All of our courses are available online and on campus, for some courses allowing students to study from anywhere in the globe while still experiencing engineering in Australia. All of our vocational programs and higher education degrees are recognized and authorized by the Australian government. But we also offer a number of courses that are specifically recognized under one of the 3 international accords, which is Sydney, Dublin, and Washington. And I'll leave it to Ms. Alexandra to take over from here and enjoy the presentation, guys. And yeah.
Thank you. All right. Good. I've seen some good mornings, good lunches, and good evenings on the chat. So welcome, everyone. Let me just throw up the slides and we can get started. All right, there we go. So, yes, my name's Alex or Alexandra. So I am in my day job a electrical engineer. However, I do also teach on behalf of EIT as well. So we will see at the end here, there's a fair few courses relating to hazardous areas that do crop up in the EIT world. So hopefully today gives you a bit of a taste as to what that entails. A bit more about myself. So as I mentioned, I am an electrical engineer in the design space, and I'm also a chartered engineer here in Australia, registered in my state and registered nationally. So all the things that we need to do as electrical engineers here in design. So let's have a look at what we're going to run through today. So bit of a welcome and introduction, but we're going to jump straight into our hazardous areas. So what exactly is a hazardous area? We're going to talk through the classification terminology, so those buzzwords that you'll hear when talking about hazardous area classification. We'll then touch on the properties of hazardous materials, so what actually makes a material hazardous in the eyes of standards. And then lastly, we'll step through what the typical hazardous area classification process is. And we will try and make time at the end for some questions, so some Q&A. So what is a hazardous area? Essentially, if you have an area where you've got the potential for an explosion, so that's the key here. So an explosive atmosphere is present or expected to be present in quantities to require special precautions. Now, when talking about special precautions, we mean if we are doing construction work, if we are installing equipment, or if we are using potential ignition sources. So that's the actual definition of a hazardous area. Now, typical things you would come across would be your refueling stations, if you do any metal grinding work in workshops, if you've got refueling not for cars, but maybe you've got aircraft hangars. In the medical side, you might have hazardous materials in your operating theatres or in your processing plant, sewage treatment plants, all of those industrial applications like gas pipelines, for example. So in each of these scenarios, you either have a hazardous material that is one of three things. It's a gas or a liquid that emits a gas. It's a dust, or in a special case, you might have methane, which is related to mining. So some other examples, we've run through a bunch of them, but now that we know that it could be a liquid or gas or dust, then thinking of the context of those refueling stations, that would be a liquid or a gas example. In the context of grinding or even, say, flour or sugar refineries, that would be a dust that could cause a hazardous area. So the standards that are applicable in Australia, which are also correlate overseas to the IEC standards, are listed here. So for each of those materials, they have their own standard. For gas, vapors, or mist, it's 60079-10-1. Combustible dusts have their own standard. Then there's a dedicated standard for those involved in electrical work, which is how you design, select, erect, or do inspections for hazardous areas. And that's part 14 here in Australia. And lastly, there's a standard that gives us some typical material properties. Now, it has been withdrawn, but it is often helpful just to get a bit of background. So a key distinction to understand is when we're talking those liquids, gases, or dusts, they do not include explosive hazardous areas. So EHA are a different form of hazardous area, and they're covered by a completely different set of standards. For example, if you work in defence, there is a dedicated standard in defence for how you classify and deal with explosive hazardous areas. Now, another trick word that people get confused is the concept of hazardous materials and dangerous goods, and they're often used interchangeably. The difference is dangerous goods is broader. So you could have dangerous goods that could be corrosive or toxic or oxidizing or water reactive, but they may not have the potential for a hazardous area. So they're slightly different. Now, if you want to classify dangerous goods, in Australia, again, there would be a relevant standard for the country that you're in. We have a dedicated standard called the Australian Code for the Transport of Dangerous Goods by Road or Rail. So essentially, there will be dedicated standards to dealing with dangerous goods that are separate to those that we deal with for hazardous areas. And that's the important distinction to take away from this slide. Okay, so how do we get an explosion? Well, if we look at the fire triangle, so let's start with the fire triangle, or the infernal triangle. If you have a flammable liquid or a gas, this triangle is how we get an explosion. So we take our fuel, which is our often the gas associated with a flammable liquid. We mix it with oxygen into a mixture that has the right balance. We introduce an ignition source, and then we get fire. So think of your old camping fire. Your fuel would be your wood, you have oxygen in the air, and you introduce your ignition source. That's what we call is the infernal triangle. So you need those three things to have an explosion. For dust, it's slightly different. We still need our fuel and our oxygen and our ignition. However, what we need for the dust is we need it to be dispersed in air and confined within a set space. Now, dust explosions are slightly different. They're often much more destructive because there is, funnily enough, more energy contained in a dust explosion than an equal amount of TNT. And what's interesting is approximately 75% of man-made dusts are actually combustible, which means they could represent a potential hazardous explosion when they're mixed with air in the right proportions and we get that dispersion and that confinement. So we mentioned earlier sugar, flour refineries as combustible dusts. You can also get grain or linen or milk powder, coal, metals. A lot of those dusts that we often produce could be combustible dusts, so you might have the potential for hazardous areas. So let's see if I can get my video to work. This is a gas explosion from 2012 in Mexico. So have a look here when we play for a pressure wave that you'll soon see is followed by a jet dispersion and a flash flyer. All right. So we could see from that video that we've got that initial pressure wave, then we get that jet dispersion, and then we get the flash fire. And it just goes to show how destructive hazardous areas can be if we do have an ignition source introduced and we get that explosion. All right, so let's talk through the classification terminology. Essentially, the first thing we do is determine what's known as our zone, and we're going to go through all of these in definitions in a second. But first step is our zone. Then we look at whether we have either a vapor and a gas or a dust. Based on that, we apply one of our zones. So they're either 0, 1, 2 or 1, 2, 3. Sorry, 0, 1, 2 or 2, 0, 2, 1, 2, 2, depending if you have gas or dust. We then assign what's known as a grouping, which is shown there. We then assign a maximum permissible surface temperature, so a temperature limit. And those are the first three terms that will be defined: your zone, your grouping, and your temperature limit. Then there's a couple of ancillary things that we'll have a look at, like the environmental factors. Do we need IP rating? Do we need to prevent it from corrosion? But the key ones are shown up here. So the zone, when we're talking about zone, it's the probability of a hazardous area forming within an area and how long it exists. So if you have a zone 0, it's very likely that you have a hazardous area all the time. If you have a zone 2, then it's much less likely, or if you do, it'll be for a very short amount of time. So zone 0 for our gas and zone 20 for our dust are the most onerous. So just to recap, 0 is where, by definition, you have an explosive gas atmosphere present continuously or for long periods. Zone 1 means it's just likely to occur. while zone 2 is where it's not likely to occur, but if it does, it should be for a very short period. So we're really going down in likelihood. Now the next one is our group, or our material group. So we've looked at the probability. Now we look at the properties of the material that are causing the hazard. So it's either group 1, 2, or 3. 1 is specifically for, again, that mining application, which we're not going to be talking about today. 2 is our gases, and 3 is our dusts. So for our gas groups, which are gas 2, there are subgroups. Now the subgroups are defined by the energy levels. So we have 2A, 2B, and 2C. Now our 2C here is the most onerous. And what we mean by that is materials classified as group 2C need the smallest amount of energy to ignite. So for reference, our 2C only needs 20 microjoules. So if you have a meter length of cable, 2.5 square mil final sub-circuit cabling, and you apply a 500 volt mega, that spark is equivalent to 20 microjoules. And that's all that's required to ignite a group 2C material. Next up from that would be 2B, which requires about 60 microjoules, and then 2A, that requires about 160. For dusts, the concept is very similar. We have 3A though, because it's dusts, 3B and 3C. Now 3C is our most onerous. So these are defined by how conductive those dusts are. So group 2C is what's defined as conductive, which is less than a kiloohm. 3B is non-conductive, 3A is your larger particles. So be wary, especially of your 2Cs and your 3C groups. So if we now put that all together, our group 1, oopsies, is our methane or our coal dust. Our group 2 is our gases, and we could have 2A, 2B, or 2C. Our group 3 is our dusts, and we could have 3A, 3B, or 3C, with the C's being the most onerous. Okay, so other materials that you might hear is the term flammable versus combustible. So flammable is the one that we care about. It means it can ignite and we can have an explosion. So if your material can ignite below 61 degrees, so if you introduce an ignition source or temperature or equipment at temperature less than 61 degrees and it will ignite that gas, you have a flammable gas. If the ignition temperature is greater than 61 degrees, you have what's known as a combustible gas or combustible liquid. Now, if your material is combustible, it is not considered a hazardous area. So you don't have a zone 0, 1, 2. You don't have a group 2A, 2B, 2C. It is not flammable. So if you have combustible liquids, you don't need any special installation requirements. If you have flammable, then you need EX rated equipment because you have that hazardous area. Now, a common application for that is on the topic of fuels. Petrol is a flammable liquid. Diesel is not necessarily a flammable liquid. You can get high flash point diesel that is therefore combustible and often considered safer. Now, other terminology, gas versus vapor versus mist. So we've mentioned you might have a liquid. There will be gas that could come off of that liquid. So a gas does not occur in liquid form. It's a gas. Your vapor is what sits right on top of that liquid, and it might be in contact with its liquid form. Whilst a mist is a cloud of condensed vapor. So all very similar, but have slightly different material properties and could all be associated with the same liquid. But there is a difference between gas, vapors, and mists. All right, so if we move on to the properties of hazardous materials. So the things that we need to know when doing a hazardous classification is at what temperature will my material automatically ignite? So we need to know this A to know if it's flammable or combustible with that 61-degree limit. But that tells us or helps us to determine the likelihood of an explosion occurring without an ignition source because that heat represents energy. Now, especially for dusts, dusts have different temperatures. So if dust is sitting in a flat layer, it will ignite at a different temperature to if it is dispersed in a cloud. So one of the things we need to know when classifying is what is the automatic ignition temperature of each of the materials we might have. The second part is slightly related, which is what is the minimum ignition energy in joules that I need to ignite my substance. So I can make sure that there is never that amount of energy that can come into contact with this flammable material. Because if I exceed that minimum energy, I'm likely to have an explosion. So I need to know what that threshold is. And the last one is what's known as flash point, still relating to ignition and energy. But in this case, our flash point is whether a flammable mixture, where we have our vapor mixed with our air in a certain quantity, is likely to occur above a liquid at a given temperature. So it's a combination of the mixture and the temperature that will cause ignition. So 3 different properties all relating to ignition and temperature or energy that we need to understand about each hazardous material we might be classifying. So for an explosion, we know we've talked about our fire triangle and our dust pentagon. In both of those, we have a mixture of a flammable material with air. So to have an explosion, we need to have the right mixture of air or oxygen with that flammable gas or vapor. So only when we have that right can we have an explosion, which also means from a safety perspective, if we can avoid that mixture, then we will not have an explosion. So the range that defines that area is what's known as our explosive limit, specifically our upper and our lower explosive limit. So if you take a concentration of material and this is the percentage here, let's make it up and call it 70%. Let's say 70% UEL is our upper explosive limit. So if you mix 70% of your material with 30% oxygen, for this material, it becomes too rich to ignite. Now let's say down here, if I take 10% of my material with 90% oxygen, if that's my lower explosive limit, then the mixture is what we call too lean, meaning there's not enough fuel in that mixture of 90-10 for it to ignite. So that's our safe zones. Between our LEL and our UEL, so between our upper limit and our lower limit, that's our explosive range. That's where the concentration of material with air is such that if you introduce an ignition source, you will get an explosion. So if we have a material that has a lower flash point, then it's obviously more dangerous. And just a distinction, gases, because they're a gas, don't have a flash point because they already have vapors, and it's vapors that could ignite. So if we look at a particular product as an example, again, let's compare petrol to diesel. So at 20 degrees Celsius, petrol evaporates, and the vapor that's formed will be in this explosive range. So your petrol evaporates, you have vapor mixing with air, creating a hazardous area. Diesel, however, wouldn't do that because it's considered a combustible liquid. Now, there are different distinctions of diesel, so don't go thinking that all diesel is combustible and therefore not hazardous, but it is just an important thing to note that you need to understand what mixtures will cause you to sit in this explosive range. So if you looked up 60079 Part 20 Part 1 or the IEC equivalent or a safety data sheet for any particular hazardous or flammable liquid or vapor gas, you'll be able to find a lot of those material properties that we were just talking about. So this extract here is taken from the standard. However, it just goes to show you could look up, say, acetone. Very common in laboratories. You might find a lot of it in a nail salon. It has a boiling point of 56 degrees, a flash point of -20. It will automatically ignite without oxygen at 465 degrees. Now we know it's a liquid that emits a gas, so it is a group 2. And based on how much energy is needed to ignite it, it's a group 2A. The data sheet will also give you your LEL and your UEL. So at 13% acetone to oxygen, above 13% concentration, you won't have potential for an explosive atmosphere. Similarly, if you're below 2%, your mixture will be too lean and it also won't have the potential to explode. But if you mix acetone with oxygen in the range of 2.15% to 13%, that's when you have your danger zone. That's when you have your mixture that could cause an explosion. So we always need to refer to the safety data sheet for the specific product. Although this table and 60079 gives some good general data, you always want to go and find the specific data sheet for the exact material that you are dealing with in your classification or in your processing plant or in your facility. So the other thing that we look at, as we know, things are all tied to temperature. So we've looked at zone, we've looked at group, now we're going to look at a temperature class. So the hazardous area, which is your mixture of material with oxygen, will have an auto ignition temperature, or an AIT. This is the temperature that can ignite the flammable gas and vapor without a spark. So we don't need that fire triangle. We don't need the dust pentagon. We can rule out an ignition source, and instead that temperature is the fuel needed to ignite. So what we need to do is, if we know the degree with which the temperature, with which that mixture will ignite, we make sure nothing around that hazardous zone can reach that temperature. And this is really important for equipment, because if we're going to put a compressor next to the thing that is producing dust, we need to make sure that that compressor doesn't reach that auto ignition temperature. So there are predefined ranges. We call them temperature zone 1, 2, 3, 4, 5, 6. Now these have defined ignition temperatures for gas and vapors, so our group 2s. So T1 is 45 degrees, T6 is 85 degrees. So if you have a gas that could ignite at, actually we have questions here. Hydrogen, as an example. If hydrogen will automatically ignite at 560 degrees, then we will need to rate our equipment to one of these T zones to make sure that it never reaches 560 degrees. So 560 degrees sits here. So in that case, we can have T1 equipment because it won't exceed 450. We could have T2 equipment because it won't exceed 300. In fact, we could have T3, T4, T5, or T6. So for a hydrogen installation, your equipment just needs to be rated to any one of those values. If we looked at ethylene, it's rated to 425 degrees, which sits about here. So if we have equipment that's rated to T1, adjacent to where we could have an ethylene release, then that equipment could reach a temperature of 450 degrees and ignite our ethylene. So for ethylene, we have to have instead equipment rated only up to T2. So T2, 3, 4, 5, or 6, because that will ensure nothing reaches 425 degrees. If we look at ethyl ether, it has an auto ignition temperature of 160. So in this example, we can't have T1, we can't have T2, we can't have T3, because equipment rated to any of those will exceed the flash point of our material. What we do need is ratings of equipment to T4, T5, or T6. And lastly, we have acetone. So at 305 degrees, we would need equipment rated to T2 or better. So that's our temperature class, which is the third piece in the puzzle. So the process now of hazardous area classification. Why do we even classify? Why do we go through this process of zones and groups and risks and distances and equipment ratings? And the reason for it is if we identify that there's a high probability that you might have an explosive atmosphere, then we can put control measures in place to make sure that either that atmosphere doesn't come about, or if it does, it won't lead to an explosion. And we do that by removing ignition sources, by reducing the ignition energy, by monitoring the ventilation, by monitoring the temperature. Any one of those control measures will then control the risk of our explosion. So the hierarchy of controls is our substitution, control, or mitigation. So if we substitute, perhaps we simply replace the hazardous substance. Maybe you can run diesel equipment and not petrol, and you immediately no longer have the risk of an explosive atmosphere. For our control methods, perhaps we can reduce the amount of flammable substance we've got, or we could limit when it would be released. We could even, this is where we do things like avoiding ignition sources, so putting in those T ratings of equipment. Or you might have additional ventilation so that you don't get a mixture within your UEL and your LEL limits. Your mitigation, this is your least preferable, we'll say, control method. So this is where you just reduce, say, the number of people who are involved in that presence, or how, if it does have an explosion, it would propagate through the rest of your system. You know, mitigation is more along the lines of your PPE. So something is going to happen, how can we just mitigate the effects of it as opposed to controlling the likelihood of having that explosion in the first place? So who can define a hazardous area? Again, it does depend on countries and legislations. In Australia, certainly, to define a hazardous area or classify it, it must be done by a competent person. Now, a competent person is someone who has a qualification to do so. And it's not any old qualification, but one that is recognised through a formal trainer. So someone does that course, obtains that certification. Now, that's how you can classify hazardous areas. To be the person to select electrical equipment to go in those hazardous areas is a separate qualification as well. So you need to also be a competent person to select electrical equipment. And if you want to conduct audits or complete inspections, that again is a separate qualification. So there's 3 different competencies or 3 different roles at play in hazardous area classification that might be the one person or that might be 3 different people. Now, those competencies in Australia, at least, are defined under 60079 Part 14. It does have a corresponding IEC equivalent, but again, it will come down to your legislation. So, the process of defining hazardous areas. First of all, we have to define what our hazard is. Then it comes down to the probability of having that perfect storm, so that material with oxygen, with an ignition source or a temperature occurring. Then we document the risks. This would be reports, these would be drawings, and these would be held by the people using that facility. So, when defining the hazard, first of all, we look at the personal influences. So, what maintenance operations do you have? What operation procedures or processes are occurring nearby? How do you evacuate from the building? So, this feeds into your risk of hazard. Does it pose a health risk to personnel? Is there a firefighting system? Is there a control room outside the hazardous area, or will you have to run into it in the event of an explosion? So that's the process side of the hazard. The second side of it is understanding the actual process itself. So what temperatures and pressures are you dealing with? What's your storage and handling process? Do you have bins? Do you have open lids of containers? Do you have storage cabinets? What is your actual process for storing and handling those materials? So once we know those two things, we then look at the probability. So this is where we do those zones, those groups, those temperature limits. So first of all, we look at where could we possibly get a release of a flammable gas or a combustible dust? And how frequent is that release? So like we spoke about zones are your probability. Is it a continuous release, like a vent, or is it an intermittent release? Do we expect it in normal operations, or is it only if something fails, like a valve fails, you might get a release of gas? We then look at the ventilation around the space, because as we know, it's about that mixture of material and air. So if we can dilute that mixture, we've got less of a probability of a hazardous area. Or if it's the opposite, and we will have a release of this material in a confined, shuttered room that has no ventilation, your probability goes up. And we define ventilation as being adequate or not adequate. And these two things will help drive what zone we have. So do we have a zone 012 in the interest of gas, or a 202122 for dust? So it seems simple enough to do, but it's all about really understanding the process. So how that material moves around your building, how it's used, what's normal operation, what's abnormal operation. If your equipment fails, what could that cause? Do we have a risk or a probability of a hazardous material in that case? Do we have risk of a hazardous zone every time we conduct maintenance because we're opening and closing things? So, for example, this is a hazardous area classification taken from our Australian standard. So you can see here, this is a typical classification or an example where we have a storage tank. It's located outdoors. So that's our tank here. Now we know it's not liquid that will explode. It's the vapor and the gas associated with that liquid that gets trapped up here within the roof of our tank. Now we have a hazardous zone associated with our vent because it's meant in normal operation to continuously release those gases. We also have a zone around our building, which is our zone 1. Zone 0, which is our most onerous, is the zone that's inside our tank. So that's our 0, that's our 1. And outside of that, we have our final zone, which is our zone 2. So in this case, it says there's a zone 2 up to a bund or a distance of 4 to 15 metres. So this is what's known as a hazardous area classification drawing, and it will form part of phase 3 of this, classification process, which is our documentation. So every time a hazardous classification is done, it typically is done in a report format. And that's because we need to record everything that goes into that resulting classification. So it gives us the background, and if the client has any comments, what assumptions we've had to use in classifying, any of those material characteristics, so what SDS we referenced, what temperature, what pressure it's run at, what our ambient is at our site, where our site is it indoors, is it outdoors, what was our assessment of the ventilation and how did that feed into the actual classification. So anything that was a basis on certifying our zones, our types, our groups needs to be recorded in our report. Now the drawings are just a really handy way of visually seeing the extent of the classification. So it's very easy to say 6 meters laterally, half a meter above every oil drum, but drawing it shows a lot more clearly what those extents are. So the drawings need to contain all that useful information. The type of zone, so is it a 012, is it 202122, the extent of that zone. We record on here the temperature class at T1, T2, T3, etc. We also put on there our gas grouping. So is it a group 2B T6 or 3A T4? So that's all very important. Now these documents are held by the people who operate that building or own and run that building, and it's a live document. So it often forms part of what's known as a hazardous area dossier, and that's what's kept by the building owner within that building. So it can be referred to, it can be updated as your processes change. If you want to change the building or change how you do a particular process, then that needs to be reviewed. So it's a constant iterative process. So if we look at some examples again, these ones are nice and coloured, which always helps. And what we're looking at is, this is an example for a flammable liquid. So here you can see we've got some pipework, and we have a zone 2 around that whole pipework because it contains valves and meters and flanges. Each one of those represents potential for a gas release, because if they fail, then you might have a leak of gas. Now they're considered adequately ventilated because they're probably outside. Here is a picture of an example of a transport truck. So you've got internal to your truck, your most onerous zone, your zone 0. So we've shown it, or it's shown everywhere inside that tank, but essentially you'll have a zone 0 above whatever that liquid level is. Now above each hatch up here, you have a zone 1. So is it normal for those to be opened? Yeah. It's likely. Are they continuously opened? No. So they're considered a zone 1. Now outside of that is a zone 2. So this is where you may get a present, but it's unlikely, it's not in normal operation, and if it is there, it's not for a long duration. So you typically have a zone 2 outside of your zone 1. And in this case, we have the tanker discharge point. So if you had to discharge the tanker of its fuel, you could open that relief valve. So it's a zone 2 because it really should never be opened, but there is a chance that it could. And the last example we have down here is where we've got a pit or a depression below ground. So if you have pits somewhere where you might have fuel spill, it makes sense that that liquid could collect in that pit. If you have a collection of flammable liquid in a pit, you're going to have a flammable vapor sitting on top of that liquid trapped in the pit. So we're going to have a zone 1. Now, this isn't in normal operation like it is a truck. So your probability of, is it there continuously, is it likely, for how long, a pit's considered a zone 1, not a zone 0. And above that, you have a zone 2. So we don't expect to have anything up here. If we do, it's very rare, it's not for a long time, so we have a small zone 1. So those are the pictures, or some example pictures, of that hazardous area classification all rolled into one. So the summary of today is to understand that you might have hazardous areas in any existing building that you operate in or in new installations. And they might be hazardous because you could have liquids, you could have vapors, you could have gases, or most commonly, you might even have combustible dusts. Now just remember that flammable is different to combustible. So a liquid might be flammable, like petrol, but not, or it could be combustible, like diesel. Now just be conscious of those terminology of throwing around hazardous and dangerous goods. There is a slight distinction between the two. Dangerous goods could also be hazardous, but not all hazardous materials are dangerous goods. Now for gas groups, we have 2A, 2B, 2C for gases depending on how much energy is needed to ignite them, and a zone 0, 1 or 2, depending on the probability. Your dusts, the concept is similar, but we have 3A, 3B, 3C, and 2, 0, 2, 1, 2, 2 for our probability in our zone. And if we were to summarize that classification process, what we want to do is define our hazards, which is our materials, the process, what is the probability of actually having a hazardous area, and then we document that. Now, the key advice is if you think you have a hazardous area, new, or you've encountered an existing one, always seek advice from someone who is deemed competent in the classification of those hazardous areas, because we've seen what explosions can look like. So always seek advice. Now, that's the last of my slides, so I will pass you back for a bit of time of Q&A and a bit of more information on some EIT courses coming up.
Thank you, Ms. Alexandra, for the lovely presentation. We'll just wait for everybody's questions, and from there we'll proceed with finishing off the presentation. So if anybody has a question, please do ask now, and Ms. Alexandra will sorry about that. Ms. Alexandra will answer all the questions needed.
Just going to see if there's any in the chat.
Oh, I see a question.
Yep, so is LEL, UEL commonly quoted as with oxygen or with air, and how do we differentiate them? The answer is oxygen, because oxygen is an actual chemical material. So we say air because it's loosely, but your air is not made up of 100% oxygen. It is a mixture itself. So when you're discussing LELs and UELs, it's oxygen and material. So I hope that answers your question. Another one from we. All right, it's commonly cited that area LEL detectors trigger at 25% of LEL. I'm not sure where the 25% comes from. It may be if you're dealing in mine sites that's methane, which is your common material. It really does depend, as we saw from that table, what your product is as to what those limits would be. So 25% may be a rule of thumb just for one thing in particular that's present, if you have a hydrogen facility or if you have a gas system, then it might just relate to that, but it's certainly not a blanket rule. Can I project the summary again? I believe, are these slides going to be made available?
Yes, they will actually.
Okay. So yeah, the summary slide will be on that. There's no commercial software for hazardous area studies, is the short answer. Unfortunately, so because it's so custom, it depends what you're doing. You might have process flow modeling if you're getting into the nitty-gritty of a detailed production facility, but there's no common software that we use. Temba, are any designs in place that can be used for safety of those not in knowledge of the hazardous gases, although in their industries? Not really. There aren't really blanket designs. There's blanket classifications within standards, so those IEC or those ASNZS Australian standards. They have example classifications. They say, like those pictures we looked at that were coloured at the end, if this is the gas you have and this is how you're using it, this is the hazardous area classification. So for your generic things like refueling stations and tankers and gas pipe work or storage houses, you can look at those as templates, absolutely. If it's custom, you'd really need to get someone involved to look at what materials and how they're used. Eugene, is the maximum permissible temperature limit the LEL? No, so the LEL is your explosive limit. It's not to do with temperature, it's to do with how much material you need to mix with oxygen, and then you introduce either auto ignition temperature or a certain amount of energy. So LEL is just that flammable mixture of oxygen to hazardous material. Oh, I've lost where I am. We had another question. When it comes to SIS testing, does an equipment EX proof spec affect its testing period? I'm not sure what SIS testing is. Apologies. So I'll have to come back to you on that one. Fire standards in Australia. We have a lot of them, Richie. It really depends if you're talking fire protection or equipment or sprinklers or smoke. They're all quite different, so I need a bit more information there. Tim, does hazardous area equipment have to be certified? Absolutely. In Australia, it's very stringent. It must be IEC certified equipment that is used. And again, there's going to be relevant standards in whichever country you're performing this in, but hazardous area equipment must be certified. You can have multiple gas groups in an installation. You might have different materials. They often just overlap. You can also have dusts with gases. You can have a combination. Out of the 3 zones, which one is the most dangerous or has the highest probability? Your zone 0 or your zone 20 if you have dusts. That's your most onerous zone with the highest probability. Now, Jean, what is the chemical composition of dust? It comes down to its conductivity. So if you have a look at that particular IEC standard for dusts, which is 10 part 2, it defines what your zones are. So 202122 is your probability. If you look at your dust groups, your 3A, 3B, 3C, it defines what properties. So for example, 3C must be a conductive dust less than 1 kilo ohms. Then you know you have a 3C group dust. Couple more questions here. I'll try and pick a few before we finish off the slide deck. Certifying authority for HA competency in AU. So it is a certificate with multiple units. It just has to be run by an RTO. So if you look up Hazardous Area Classification and make sure it's from an RTO, this is Abdul's question, then that's the would be an okay training body to get your Hazardous Area Classification certification through. Welter, a cooking gas we use in industrial kitchens. Could be LPG, not sure. If it's LPG, that is a flammable gas and would have a hazardous area associated with it. However, typically it's installed at such a low temperature that you're unlikely to get those releases. So you only really have hazardous area at your storage of LPG, not on your pipework or in your kitchen. But again, that's the Australian way to classify. It would depend on where you are. All right, I might have to stop it there because I know there are a final few slides to get through, but hopefully that answered, I think, most of people's questions. So yeah, thank you for that.
Thank you very much, actually. If you have any questions to still ask, I'll drop the email in the chat box shortly. Our upcoming courses. We have a range of courses in civil, electrical, mechanical, and industrial automation engineering. To see our full list of our courses, I'll drop the link in the chat box just now, shortly. Give me a few seconds. So there's the link in the chat box for those that are interested in our upcoming EIT courses. And our upcoming webinar is called Data-Centric Evolving Power Grids, which will be happening on the 16th of February. So please keep up to that. And I'll also drop the link to the webinars, the upcoming webinars, in the chat box. And if you're interested in more webinars, you can always go to the link and check out the upcoming webinars. And I just dropped the link in the chat box for those that are interested in the upcoming webinars. And the certificate of attendancy. To receive your digital certificates of attendancy for participating in this webinar, please fill out the form and survey or scan the QR code. I will put the link in the chat box just now. I'll leave this for a few minutes for everybody to scan or get the QR code. If you still have any questions to ask Dr. Alexander, Ms. Alexander, or anything about EIT, I will put the link to I will put our email address in the chat box, and you can ask any questions regarding EIT or the whole presentation that was happening on today. Okay, guys, thank you very much for attending this presentation today. And thank you, Ms. Alexandra. This was a lovely presentation, and I also got to learn something new, honestly speaking. And thank you. Thank you again for the presentation. And this is where I leave everybody. And thank you, guys. And have a good day, have a good night, and thank you.
Thanks, everyone. Have a good night.